Sitting just 4.2 light-years away in the southern sky, Proxima Centauri is the closest star to our Sun. While its proximity makes it a primary target for interstellar ambitions, its behavior reveals a volatility that challenges the very concept of a celestial neighbor. In 2016, astronomers found a rocky world orbiting that star. Proxima B has roughly the mass of Earth, and the discovery ignited global excitement about finding a twin to our own planet. The optimism made mathematical sense. Red dwarfs like Proxima Centauri are the most common type of star in the galaxy, and they burn their fuel so slowly that they can live for trillions of years. That timeline offers a massive window for biology to evolve. This diagram illustrates a star's habitable zone. It highlights the specific distance, often called the Goldilocks ring, where temperatures are moderate enough for liquid water to theoretically pool on a planet's surface. Proxima B orbits right inside this green band. Calculating a habitable zone only accounts for temperature. It completely ignores the violent, destructive behavior of the red dwarf itself. A comfortable temperature does not mean a planet is hospitable. The more we look at our closest planetary neighbor, the more we realize it operates like a cosmic executioner. Proxima Centauri emits less than 1% of the energy our Sun produces. Because it is incredibly dim, its habitable zone is compressed severely close to the stellar surface. This scaled comparison maps the orbits of Mercury, Venus, and Earth. When we overlay Proxima B's path, you can see the severity of its proximity. It orbits nearly 8 times closer to its star than Mercury sits to our Sun. That extreme proximity causes a mechanical consequence called tidal locking. The planet's rotation perfectly matches its orbit, forcing one specific hemisphere to point directly at the red dwarf forever. The resulting landscape is a physical nightmare. The day side is baked at temperatures exceeding 400 degrees Celsius in permanent red daylight, while the far side is entombed in pitch-black eternal night. The only theoretical place a life form could survive is a narrow twilight strip running between the boiling day and the frozen night. Yet any chance of survival there depends entirely on the planet maintaining a stable atmosphere. The orbital geometry alone guarantees an intensely hostile environment. It forces the planet to rely on an atmospheric shield that the star is actively working to destroy. Proxima Centauri is classified as a flare star. It operates with a tangled, highly volatile magnetic field that erupts with terrifying frequency. In March 2016, telescopes captured the star surging in brightness by a factor of 68. For a few fleeting seconds, this dim speck released enough energy to become visible to the naked eye on Earth. The eruptions only escalate. In 2019, observations recorded a sudden, violent event where the star's ultraviolet brightness multiplied by 14,000 in just 7 seconds. This cross-section shows how these daily barrages dismantle a planet's atmospheric defenses. Mathematical models calculate that hitting a planet with this frequency systematically strips away 90% of its ozone layer in just 5 years. Without that protective shield, the radiation pounds the surface directly. A single superflare hits the ground with 100 times the lethal dose of UV radiation required to kill Earth's toughest organisms. Daily superflares transform the twilight zone into an irradiated shooting gallery, executing any biology attempting to take hold. While the superflares act as sudden, acute explosions, the star also inflicts a chronic, grinding malice through its stellar wind. This is where tidal locking creates a fatal vulnerability. The planet's slow rotation prevents it from generating an internal magnetic dynamo, leaving it without a deflector shield to repel incoming particles. This diagram visualizes the mechanics of the stellar wind. Hitting the atmosphere with 10,000 times the pressure Earth experiences from our Sun, the wind directly heats hydrogen, oxygen, and nitrogen atoms, dragging them permanently into deep space. There is an ancient, cruel twist to this process. Red dwarfs burn incredibly hot in their youth. Any primordial water Proxima B possessed was baked off hundreds of millions of years before the star settled into its current state. The planet was cooked long before the temperature ever normalized. Even if an organism could somehow survive the intense radiation, the stellar wind ensures it would suffocate, leaving behind a completely dead, airless rock. Observations of Proxima B and systems like TRAPPIST-1 suggest these worlds exist as sterilized, roasted cinders, requiring a complete reevaluation of the label Earth-like. This reality takes on a massive scale when you look at galactic statistics. 75% of the stars in our galaxy are these volatile red dwarfs. The tens of billions of rocky exoplanets we hoped might be sanctuaries are likely part of a massive, radiation-soaked galactic graveyard. Our fastest probes would take over 6,000 years to reach Proxima Centauri. But even if we could cross that distance, the physical barriers of the star system mean humanity can never touch these worlds anyway. We are forced to look back at our own solar system and frame it against the extreme hostility of the wider cosmos. Proxima Centauri stands as a stark warning of how miraculously fragile and rare Earth's existence truly is, in a universe not designed for our survival.